In the previous lecture, we have discussed the spin angular momentum of Dirac particle, and you have seen that a particle which obeys Dirac equation has definitely a spin angular momentum. And when you say spin angular momentum, that is an intrinsic angular momentum not associated with any type of motion of the particle. Okay, just like mass and charge, which are intrinsic property of a particle, this spin is also an intrinsic property. But you know that whenever a particle has angular momentum of any type, definitely associated with that angular momentum, the particle has magnetic moment. Okay, so as the Dirac particle has a spin angular momentum, so you can definitely say that such particles will have the magnetic moment associated with the spin angular momentum. Okay, and as the Dirac particle will have a magnetic moment associated with its spin angular momentum, so a Dirac particle just behaves as a tiny magnetic dipole. Okay, and you know, whenever a magnetic dipole is placed in an external magnetic field, there is an interaction between the dipole and the external field, and magnetic energy is developed in it. Okay, and that energy is actually affected, or energy level is affected due to the spin orbit interaction. When you say spin orbit interaction, that means there will be an interaction between the magnetic field and the spin angular momentum and its associated magnetic moment, orbital angular momentum and associated magnetic moment. So definitely if the Dirac particle, particularly the Dirac particle which has actually charge, when such particle will be placed in an external magnetic field, then definitely there will be a spin orbit interaction. So we will discuss now two important results or two important facts regarding this Dirac particle. In this video, you will see the discussion on the magnetic moment of Dirac particle, and in the forthcoming lecture, just in succession, we will discuss the spin orbit interaction. Okay. In fact, this concept is also known as Dirac equation in electromagnetic field. It means when you will place the Dirac particle in an electromagnetic field, then you will see that the momentum and energy of the particle gets modified, and accordingly the form of the Dirac equation will also change. Okay. So first of all, to discuss the magnetic moment associated with the spin angular momentum of Dirac particle, we will see what will be the Dirac equation when we place the Dirac particle in an electromagnetic field. You know, an electromagnetic field is characterized by two potentials, in which one potential is called magnetic vector potential, denoted by the symbol vector A, and the another is called a scalar potential, denoted by the symbol phi. We have studied these potentials in your course on electrodynamics, and if you have not studied, I will suggest you watch my video in the playlist of classical electrodynamics, and you will find a detailed discussion on these electromagnetic potentials there. Okay, but you have definitely watched, as I hope. In fact, you have also seen in the previous lecture the Klein-Gordon equation in an electromagnetic field. So same procedure will be followed here. You know that if A is the magnetic vector potential and phi is the scalar potential, then the momentum operator will get modified like this. This will be P hat equal to P hat minus EA over C, where E is actually charge of the particle and C is, you know, the speed of electromagnetic wave in free space. And this result can also be written like this. This is Cp equal to Cp minus Ea. I am not pronouncing this hat always. I will speak P, but that means P hat, because P is here not momentum, but the operator associated with momentum, okay? Because you know in quantum mechanics, all observables are always written in terms of the associated operator, okay? And similarly, the energy in this case, when the particle will be placed in electromagnetic field, will be given by E minus E phi, where phi is the scalar potential. So when we will write the Dirac equation in electromagnetic field, what we will do? We will simply replace P by P minus Ea by C, and E will be replaced by E minus E phi. And then you will get the Dirac equation in electromagnetic field. So first of all, write the Dirac equation when the particle is not in an electromagnetic field, and then modify the terms. So you know the original Dirac equation when you not talk about the electromagnetic field is given like this. This is C alpha dot P plus beta mc square psi equal to E psi. I am not pronouncing that hat, okay? But this expression can also be written like this. This is E minus C alpha dot P minus beta mc square psi equal to 0. Simply we take the terms in LHS in RHS, and then this equation results. Now, if the particle is placed in an electromagnetic field, you have seen that this energy operator will now become E minus E phi, okay? And you know, you have seen that this C times P, Cp is equal to Cp minus Ea. So this term C alpha dot P will be modified as alpha dot Cp minus Ea, okay? And beta mc square at each. So this is Dirac equation in electromagnetic field. As I have told you that all the observables here like E and P are actually the operators associated with the energy and momentum. And so here this E hat means IH bar del del T, and P hat means minus IH bar del, okay? But we will not use this operator form of this. We will simply use the symbol E hat and P hat for the energy and momentum operators, okay? So this is this equation 1 actually is the Dirac equation in an electromagnetic field, okay? Now, to get the idea of magnetic moment associated with the Dirac particle, which is due to the spin angular momentum of the particle, we have a lot of algebra, lot of calculation, but when you will watch the video seriously, step by step, everything will be clear. So there will be a mathematical step to get such a result, and you have to in fact remember all those steps by practice. So to get the result, you can see in Dirac equation the operator is E minus E phi minus alpha dot Cp minus Ea plus beta mc square. This is operator, and this is operated on psi, and that is equal to 0, okay? Now we will use a particular algebra. In fact, we will multiply this equation 1 from left side, or you can say we will operate an operator from left side on equation 1, and that operator will be E minus E phi plus alpha dot Cp minus Ea plus beta mc square. It means we will change the sign of the second and third term and then operate that operator on it from left side. You can also say that we will multiply this equation from left side by this operator. You can see E hat minus E5 plus alpha dot Cp minus Ea plus beta mc square. Okay. So you can see the operator by which we have to multiply is E minus E5 plus alpha dot Cp minus Ea plus beta mc square. And the equation in the LHS of equation 1 was E minus E5 minus alpha dot Cp minus Ea minus beta mc square psi, and that will be equal to 0. Okay. Now operate this operator which has been written in the first square bracket on this operator written in the second inside the second square bracket. You can see when E minus E5 will be operated on E minus E5, that will be E minus E5 square. And when this alpha dot Cp minus Ea will be operated on minus alpha dot Cp minus Ea, you can see that will be minus alpha dot Cp minus Ea square. And this beta mc square will be also operated on this minus beta mc square. Okay. So that will be beta square m square C4. But you know, you have studied in the previous lectures that the square of this beta matrix is equal to 1. Okay. So I have not written here beta square because that is equal to 1. So this is simply minus m square C4. Okay. Now the another term will be what? In fact, some of the terms will cancel out. So now take the operation of E minus E5 on the second term, that is alpha dot Cp minus Ea. So this will be minus E minus E5 alpha dot Cp minus Ea. Okay. And now as it is and these are operators, so don't think about the general multiplication of algebra because here order matters. So now we will take the operation of this term this minus alpha dot this alpha dot Cp minus Ea will be operated on this E minus E5. So this is alpha dot Cp minus Ea operated on E minus E5. Okay. And the remaining terms will actually vanish when you will take the operation of this beta mc square on other terms except this minus beta mc square, that will vanish. So I have not written it here. Okay. I think you are getting the things. Now, in the previous lecture on illustrative examples of Dirac matrices, I have solved a very important problem, and I have also told you that such results are very invariably used in your further discussion. And you have seen, you can see the first lecture on the illustrative example of Dirac matrices, and there you will find this problem. In fact, this is an identity, and we have seen the proof of this identity in the previous lecture. And what is that identity? This is alpha dot b times alpha dot c equal to b dot c plus I sigma dashed dot b cross c, where sigma dashed is actually a spin operator, and this spin operator or a spin matrix, you can say, this is defined like this. This sigma dashed is equal to a 4 by 4 matrix. 4 by 4 matrix, because sigma is here the Pauli spin matrices, which is 2 by 2. So each term each element in this is actually a 2 by 2 matrix. So this is a 4 by 4 matrix. Okay, and I think you can remember this problem or this result because I have discussed this result in very detail in my lecture in my first lecture on the illustrative example on Dirac matrices. Okay. In fact, in this result, you have seen that this ordinary vectors B and C commute with alpha, but necessarily they do not commute with each other. When you say that this B and C commute with alpha, it means commutator of B with alpha and commutator of C with alpha are 0. But the commutator of B and C may or may not be 0. So it is not necessary that B and C commute with each other, but definitely these vectors B and C commute with alpha, where alpha is Dirac matrix. Okay. So in this identity, now we will take B and C equal to Cp minus Ea. B is also Cp minus Ea and C is also Cp minus Ea. We will take, it is not on the basis of equation 2, but since we are, our aim is to simplify each term in the LHS of equation 2. So simplifying each term, in first step, we take B and C equal and both equal to Cp minus A. You will take, see here. Now, B and C are replaced by Cp minus Ea. Okay, Cp minus Ea. In fact, then what will be this identity? You can see alpha dot B and alpha dot C, but you are taking B and C equal, and that is equal to, in fact, Cp minus Cp minus Ea. Okay, so both of these factors will be same because B and C are same. So this will be simply alpha dot B square, but B is taken as Cp minus Ea. So this will be alpha dot Cp minus Ea square. Okay. So you can see I have written it here. This is alpha dot Cp minus Ea whole square. Okay. And in RHS you can see there is B dot C, but B and C both are not same. We have considered it is not necessarily same, but we have considered that B and C are same, and that is equal to Cp minus A. So this will be simply B square. Okay, because a scalar product of two vector, a scalar product of a vector with itself is equal to a square of that vector. So that will be simply Cp minus Ea whole square. You can see. So the first term is Cp minus Ea whole square. And what is the second term? Second term is I sigma dashed dot B cross C. But we have assumed that B is equal to Cp minus A and C is also equal to Cp minus A. Okay. So I have substituted here at the place of B and C, Cp minus A. Okay. Now we will simplify this vector product Cp minus Ea cross Cp minus Ea. You can think that if Cp minus Ea is an ordinary vector, not in fact operators, then the product will be 0 because the vector product of two similar vectors or identical vectors is always 0. But here, since this Cp minus Ea is not a vector quantity, but these are operators, so you cannot say that this cross product will be equal to 0. So first of all, we will see this product is equal to what? Cp minus Ea cross Cp minus Ea. What will be this? Now, take the product. we will first of all take the product of Cp hat with Cp hat. So this will be C square P hat cross P hat, okay? And then Cp cross minus Ea. This will be minus Cep cross A. Now, minus Ea cross Cp. So this is minus Cea cross P, okay? And minus Ea cross minus Ea, that will be plus E square A cross A, okay? Now this P cross P is equal to 0, this A cross A is also equal to 0, okay? So the first and last term is 0, and in this remaining two terms, you can see we can take this minus Ce as a common factor, and that will be, and then the remaining terms will be A cross P plus P cross A, okay? So this is simply minus Ce times A cross P plus P cross A, okay? Now, we have to know the meaning of this operator. This is an operator, remember, A cross P plus P cross A, this is an operator, and our aim is to cast this operator in a simpler form, and for that we will operate this operator on the wave function psi. So A cross P plus P cross A is operated on psi, then what will be the result? You can see this will be A cross P psi plus P cross A psi, okay? Now you know that this momentum operator P hat is equal to minus I h bar del psi. So this is A cross minus I h bar del psi. And again this momentum operator P hat has been written as minus I h bar del and cross A psi, okay? Now the first term remains same. You can see this is minus A cross I h bar del psi and minus I h bar, but see here, in fact here there is del cross A psi. Del, when you say del cross, that means curl of A psi, where psi is a scalar and A is a vector. And you know that curl of the product of a vector and a scalar is equal to what? This is psi times curl of A plus gradient of psi cross A, okay, cross A. You have definitely studied this vector identity in your course on mathematical physics in vector analysis. So curl of A psi has been written like this. This is psi del cross A plus del psi cross A. Del psi means gradient of psi and del cross A means curl of A, okay? So instead of del cross A psi, I have written here psi del cross A plus del psi cross A, okay? Now again this first term remains at ease, and see here this is minus I h bar psi del cross A, this remains at ease. But you know that the vector product of two vectors is not commutative. A cross B, you know, is equal to what? A cross B is equal to minus B cross A, you know. And so this del psi cross A can be written as minus A cross del psi, okay? Now see, this is minus A cross I h bar del psi minus I h bar psi del cross A, and minus minus plus, this is plus A cross I h bar del psi. So this first term and the last term will cancel out, and your result is simply minus I h bar psi del cross A, that is curl of A. So finally you can write this expression as A cross P plus P cross A psi is equal to what? let us see, the page has been turned, but this will be just okay, don't worry, I am telling you several times, so don't get bothered. This will be minus I h bar del cross A psi, okay, and hence you can say that A cross P plus P cross A is equal to minus I h cross del psi. So I have casted this operator A cross P plus P cross A in this form. This is in fact minus I h bar del cross A. Okay. Now we will make the use of this expression which I have obtained in this equation 6 in equation 5. So let us see what is your equation 5. This is your equation 5, and you can see in RHS there is A cross P plus P cross A, and you have obtained the value of A cross P plus P cross A. So we will set that value in the RHS of this equation 5 after multiplication by minus CE. Okay. So you can see the LHS of the equation number 5, and we have obtained the meaning of this operator A cross P plus P cross A. So let us substitute it. Okay. See, this is LHS of equation 5, Cp minus Ea cross Cp minus Ea, and that was equal to minus Ce times this much, but this much is equal to IH cross IH bar del cross A. So instead of this I have substituted here minus IH bar del cross A. Okay. Now this minus minus will become plus, and this can be written as ICEH bar del cross A. Okay. But you know, you have studied in your course on electrodynamics that this del cross A is equal to B. Actually, this is the defining equation of the electromagnetic vector potential A. So it is actually del cross A is equal to B, where B is the magnetic field. This equation is just defining equation. When you have studied in your course on electrodynamic potential in electrodynamics, definitely you have observed this equation, this result, that is del cross A, curl of A is equal to B, and that's why we say that this A is the generator potential of magnetic field. Okay. Because curl of A is equal to magnetic field B, so this potential A is called generator potential of magnetic field. Okay. So so at the place of del cross A in this result, we can substitute B, where B is magnetic field. So substituting this value, your result is Cp minus Ea cross Cp minus Ea. This is equal to ICEH bar B. Okay. Now we will substitute this value of this product which we have obtained in equation 7 in equation 4. So let us see what will be our result which has been defined in equation 4. See the equation number 4. Where is equation 4? See, this is your equation number 4. See here. In LHS there is alpha dot Cp minus Ea whole square. In RHS there is Cp minus Ea square plus I sigma dashed dot this much. And we have actually obtained the value of this Cp minus Ea cross Cp minus Ea. So at the place of this Cp minus Ea cross Cp minus Ea, we will use the result which we have just obtained. Okay. So see the equation number 4 and write all the terms now. See here. This is the LHS of equation 4 you have just seen. This is alpha dot Cp minus Ea square, and in RHS the first term was Cp minus Ea square, and plus I sigma dashed dot this much, but this much is now equal to what? This is ICE h bar b. So instead of that factor, I have written here ICE h bar b. Okay, and this I times I will be I square, and you know I square is equal to -1. So you can write it equal to Cp minus Ea whole square minus Eh bar C sigma dash dot B. Okay. So we have simplified one of the terms in the RHS of that equation number 4. Okay. In fact, now the remaining two operators in equation 2 will be also simplified. Step by step, you can see what are the remaining operators in this equation. You can see I have actually simplified this remaining operator are, the last two operators are E minus E phi alpha dot Cp minus A. This is the third operator in this equation, and plus alpha dot Cp minus Ea times E minus E phi. Now we will simplify these two last two operators. This is just a simplification, so there will be some mathematical steps. You can see the last two operators are minus E in minus E phi alpha dot Cp minus A and plus alpha dot Cp minus A times E minus E phi. You have seen. Now let us see what will be this. I have actually skipped some of the terms here because that will cancel out. You can see when you will take the product minus E alpha dot Cp minus Ea. See here, E minus E alpha dot Cp minus Ea. Okay, and in the second term you can see this is E plus E alpha dot Cp minus Ea. You can see both of these two terms will cancel out. So I have not written this term here. Okay. Now the remaining terms will be what? You can see when you will take the product of this minus E with minus E alpha with this minus Ea. So minus will plus, and this will be E alpha dot Ea. Okay, and similarly in the second term there is minus E alpha dot Ae. So E alpha dot Ea minus A. Okay. Now take the product of this term containing phi and p. So this will be Ce alpha dot phi p minus p phi, and except these terms, other terms will actually cancel out as I have told you, and so our result remains this. Okay. Now you can see Ea minus A, E and A both are operators. So this is just the commutator of E and A. So this first term is written as E alpha dot commutator of E and A. And similarly, this phi p minus p phi, this is commutator of phi with p. Okay. So our result becomes E alpha dot commutator of E and A plus CE alpha dot commutator of phi and p. Okay. But you know, you have studied the videos on the quantum equation of motion when you have studied the Heisenberg picture in the previous lecture. Then you have seen there how to write the equation of motion in commutator form. You know, if E and A are the operators and its commutator is E with A, then according to Heisenberg picture, you have learned that this can be written as I h bar del A del T. And similarly, this commutator phi and P is written as I h bar del phi. Here the operator will be with respect to the this P, so this is del phi. Okay, and this E is just like Hamiltonian, and so this is defined as I h bar del A by del T. You know. Now to cast this result in a suitable form, we take simply minus I E h bar C alpha dot as a common factor. Okay. So you can see in the second term this is present except this minus sign, and but in the first term there is not C present, so we will divide the first term by C, and since we have taken minus as a common factor, but both the terms in this equation is positive, so we will take both terms now negative. Okay, so this is minus I h bar C alpha dot minus 1 by C del A by del T and minus del pi. Okay. But when you study the electrodynamic potentials in electrodynamics, you know that electric field vector is given by E equal to minus del phi minus 1 over C del A by del T. Okay. If the field is not conservative, if in case of conservative field, this, yes, you can say conservative. If the field is electrostatic, then it is conservative, and then E is equal to simply minus del phi. But if this field has been produced due to the variation of magnetic field, which is called electromagnetic field, then E vector is defined like this. This is minus del phi minus 1 over C del A by del T. So instead of this minus 1 over C del A by del T minus del phi, this we will write simply the electric field vector E. E is actually what? This is electric field vector. Electric field vector. Don't confuse it with the energy E. Okay. So the last two operators in that equation has been simplified in this form. Okay. Now we will use this result which we have obtained just now in equation 8 and 9 in equation 2. Okay. So I am showing you the equation number 2 C and substitute those values here. You can see in our equation 2 it reads E minus E phi square minus alpha dot Cp minus Ea square minus m square C4 minus E phi alpha dot Cp minus Ea plus alpha dot Cp minus Ea times E minus E phi psi equal to 0. And you have actually simplified this term alpha dot Cp minus Ea whole square, and we have also simplified this term in last two operators. Okay, so making these substitutions which we have obtained here, in this equation number 2, our result will be what? You can see it here. E minus E phi whole square is at is, okay? And at the place of the second term, we write this much because you have obtained it. This is minus Cp minus Ea whole square minus Eh bar C sigma dash dot B, and minus M square C4 is at is. And for the last two operators, we have obtained this is equal to this much, IEH bar C alpha dot E, and that will be operated on psi, and that is equal to 0. So this is actually the Dirac equation in electromagnetic field, you can say. Okay. Now I have simplified this result to some more extent. You can see this can be written as E minus E phi square minus Cp minus Ea square minus M square C4, and plus this minus and this minus will now plus Eh bar C sigma dash dot B, and minus IEH bar C alpha dot E is operated on psi equal to 0. Okay. In fact, in the previous lecture, we have discussed the Klein-Gordon equation in an electromagnetic field. That is also called the relativistic wave equation in electromagnetic field. And you can see the first three terms, that is E minus E phi whole square minus Cp minus Ea whole square minus M square C4. These three terms were present in the relativistic wave equation in electromagnetic field. Okay. So the remaining two terms, that is Eh bar C sigma dash dot B minus IE H bar C alpha dot E. We have to understand what are the physical significances of these two terms. Okay. Actually, to know the physical significance of these last two terms in this equation 10, we have to take the non-relativistic limit of the entire equation defined in equation 10. After taking the non-relativistic limit, we can identify, we can actually understood what will be the meaning of these last two terms. Okay. One thing is clear, that these terms are related to the electric and magnetic field, and so definitely this will since the operators are energy operators, so definitely these terms will have definitely related to the electrical energy and magnetic energy. Definitely you can hope. Okay. In fact, in non-relative, if your aim is to cast this equation in non-relativistic form, then you have to think that in non-relativistic limit, this energy operator is equal to E hat plus mc square, where this E hat should be much smaller than the rest mass energy of the particle in case of non-relativistic limit, and this E phi should be also much smaller than mc square. Okay. So when we will replace E by E plus mc square and take the limiting condition that E dashed is much smaller than mc square and E phi is also much smaller than mc square, then this equation defined in equation 10 will be converted into its non-relativistic limit. So let us write this equation in this condition. And for this, first of all, we will simplify this term, E minus E phi whole square. As you know, in non-relativistic limit, E should be replaced by E hat plus mc square. So this can be written as E hat plus mc square minus E phi whole square. Now, take this m square c4 as a common factor. As this mc square is present inside this square, so when we will take this mc square outside of the bracket, there will be m square c4. Are you getting the things or not? mc square is inside the bracket, and the, over the bracket there is a power 2. So when you will take this mc square as a common factor in outside, then that will be m square c4. Now, at the place of mc square, we will now write 1, okay? And e dashed minus e phi will be divided by mc square, because this e dashed minus e phi does not contain mc square, okay? Now, since you know that this e dashed minus e phi, this will be actually much smaller than mc square in a non-relativistic limit. So we will make the binomial expansion to the first approximation. 1 plus x to the power n is almost equal to 1 plus nx, but only when you say that this x is much smaller than 1. Here, since e dashed minus e phi is much smaller than mc square, so e dashed minus e phi divided by mc square will be much smaller than 1. So when you will expand this in binomial expansion, you have to take this first approximation. This is called first approximation, okay? Here in our present problem, at the place of n there is 2. So after making this first approximation of binomial expansion, you will get the result m square c4 times 1 plus 2 e dashed minus e phi over mc square, okay? Now multiply by this factor m square c4 to the terms inside the bracket. This will be m square c4 plus 2 times e dashed minus e phi times mc square, because one of the mc square will cancel out, okay? So in the non-relativistic limit, we have simplified this term e minus e phi whole square minus m square c4, and that is simply I have taken this m square c4 in LHS, and so in non-relativistic limit you can say that this e minus e phi whole square minus m square c4 is simply equal to 2mc square e dashed minus e phi. So when you will substitute this much 2mc square e dashed minus e phi at the place of this e dashed minus e phi whole square minus m square c4 in your result, then that equation 10 will be converted into its non-relativistic limit, okay? So let us see once this equation number 10, you can see e minus e phi minus e minus e phi whole square minus m square c4. Instead of this term which I am just crossing, you will put the result which you have obtained, and the other result will remain same, you can see. So instead of those two terms, I have written 2mc square e dashed minus e phi. The remaining terms are e this minus cp minus e whole square plus ech bar sigma dash dot b minus IEH bar C alpha dot E, okay, and operated on side, that is equal to 0. Now take this term 2mc square e dashed, okay, and the remaining terms will be written now in RHS. When you will bring the all other terms in RHS, the sign will be just reversed. So you can see, we can write this expression as 2mc square e dash psi equal to what? When this term minus cp minus ea whole square will be in RHS, that will become plus cp minus ea whole square, okay? And this 2mc square times minus E phi, and this will be plus 2mc square E phi in RHS. Okay, and EC h bar sigma dash dot B, when it will be in RHS, this will be minus EC h bar sigma dash dot B, and this negative term will be now positive in RHS. Okay. Now, what will be this E dash psi? So we will divide the RHS of this equation by this 2mc square, you can see. Now, in this first term, take this c as a common factor. Since there is a square, so when you will write it in outside of the bracket, this will be c square. So c square over 2mc square and into p minus Ea divided by c, because c is not present in this equation, in this term Ea. Okay, and plus when you will divide this 2mc square E phi by 2mc square will cancel out and the term remains E phi. And when you will divide this equation, let us say this will be also divided by 2mc square, and this is also divided by 2mc square. Okay, and here this c square and c square will cancel out, and here this c and c square will cancel out, and also here this c and c square will cancel out. Okay, so what will be our result after simplification? You can see this will be actually equal to E dash psi equal to 1 over 2m p minus Ea by c whole square plus E phi minus Eh bar by 2mc sigma dash dot b plus IEh bar over 2mc times alpha dot E, and that is equal and operated on psi. Okay, so in non-relativistic limit, the Dirac equation in an electromagnetic field is like this as defined in equation 12. Okay, now you know that the Schrodinger equation for a free particle will be what? You know, Schrodinger equation is given as E hat psi equal to H hat psi. Okay, now H hat, this is in fact T plus B, this is P hat square over 2m psi. In non-relativistic case, this Hamiltonian is kinetic energy plus potential energy. This is kinetic energy operator, and don't write psi first of all. See, Hamiltonian will be P hat square over 2m plus V of R, and that will be operated on psi. But as you are considering a free particle means particle free from interaction, and in case of a free particle, since the particle is free from interaction, so this potential function vanishes, this is 0. So for a free particle, the Schrodinger equation will be simply E hat psi equal to P hat square over 2m psi. So I have written here that this Schrodinger equation is E hat psi equal to P hat square over 2m psi. Okay. Now, if you compare this equation, this is actually the Schrodinger equation when our particle is not in an electromagnetic field. But since we are talking about the wave equation in electromagnetic field, so now we will write this Schrodinger equation when the Schrodinger particle will be in an electromagnetic field. You know, in this case, E is replaced by E minus E phi, okay? And momentum P is replaced by P minus EA over C, okay? So we will substitute E minus E phi at the place of E when you are talking about the Schrodinger equation for a free particle in an electromagnetic field, okay? And in RHS you can see there is 1 over 2m, and instead of P hat square, now we will write P minus EA by C whole square operated on psi, okay? Now rearrange the term. You can see this equation can be written as E hat psi equal to E phi plus 1 over 2m P minus EA whole square operated on psi, okay? Now we will compare this equation 12 and this equation 13, okay? You can see that this E at the place of E hat, E dashed, there is E here. At the place of E dashed in equation 12, there is E hat in equation 13, okay? And 1 over 2m times P minus E whole square is already present here, okay? So there are two extra terms in this equation 12, okay? Actually these two extra terms is associated with the spin of the particle. You know, Schrodinger equation does not tell anything about the spin of particle. Schrodinger equation, when was developed, the spin of the particle has been not taken into consideration, okay? But when you will take the spin of particle under consideration, then in an electromagnetic field, the wave equation for a free particle is not like this which Schrodinger equation says, but that will be like the Dirac equation which have been defined in this equation 12, okay? So what actually these two extra terms refer? You will see that this term minus EH bar over 2mc sigma dash dot B, this is actually related to the magnetic field and spin of the particle. This is a spin operator, you know, sigma dash. And so this term actually represents an energy which is called magnetic energy, okay? And the term containing E, that is electric field, this represents the electrical energy of the particle, okay? And since both of these are associated with a spin of the particle, that's why these two terms do not come into the picture when we talk about the Schrodinger equation, because in Schrodinger equation, you know, the spin of the particle has not been taken under account, okay? So what will be the magnetic energy and the electrical energy? Now you can see. If you say that due to this interaction, the magnetic energy developed is represented by UM, then UM is equal to what? You can see the equation. This is minus EH bar by 2mc sigma dash dot B, sigma dash dot B. But you know, the classical expression for the magnetic energy of a magnetic dipole placed in an electromagnetic, placed in a magnetic field is what? This is actually studied in the classical physics, even in the +2 level. You know, the magnetic energy is given like this, UM equal to minus mu dot B, where mu is actually called the magnetic dipole moment. So when you will compare these two equations, you know that the classical expression for magnetic energy of a dipole placed in an external magnetic field B is equal to minus mu dot B, and we have obtained here that the magnetic energy of the Dirac particle when it is in an electromagnetic field is given like this. This is minus 2e minus EH bar over 2mc sigma dash dot B. At the place of B, you can see there is B here too. So definitely the remaining factor represents the magnetic dipole moment of the Dirac particle. So the magnetic moment of the Dirac particle will be mu, and that mu is equal to EH bar over 2mc sigma dashed. You can see that this mu is directly related to the spin of the particle. Okay, and from this result you can easily say that the Dirac particle has magnetic moment due to its spin angular momentum. Since the particle has a spin angular momentum, so associated with that very spin angular momentum, Dirac particle has magnetic moment. So magnetic moment is confirmed by the Dirac equation or by Dirac theory. You can see. Okay. Now, the second term containing the electric field vector E will in fact represent the electrical energy of the Dirac particle. So this is given by UE equal to IEH bar over 2mc alpha dot E. But again, you know, when an electric dipole is placed in an external electric field, the electrical energy of interaction developed in the dipole is given by this formula. This is minus PE dot E. Actually here this PE is called the electrical dipole moment of the electric dipole. Yeah, dipole moment of the electric dipole. Okay. So comparing this, you can see at the place of E already there is E. So the electrical dipole moment of Dirac particle is PE equal to minus this will be minus IEH bar over 2mc times alpha. Okay. But in fact, in most of the practical cases, it is seen that this electrical energy or this dipole moment PE is actually negligibly small. So we do not take into account this electrical dipole moment of the Dirac particle, and we simply say that Dirac particle has actually the magnetic moment. Okay. In fact, in most of the practical cases, this term which represents the electrical dipole moment of Dirac particle is of the order of V over C square. And you know, in case of non-relativistic motion, this V is much smaller than C, and so this V by C whole square will be very small, and PE is of the order of V by C whole square, and so this will be just negligible. And that's why we simply say that the Dirac particle has associated magnetic moment. We not talk about the electrical dipole moment of the Dirac particle. Okay, so I think that the concept of the magnetic dipole moment of Dirac particle or the Dirac equation in electromagnetic field is now clear to you. If you will watch the video seriously, everything will be clear. There is a lot of mathematics here, but when the concept will be developed, I deal actually all the steps clearly so that you can easily understand the facts. But when your concept will be developed, everything will be crystal clear to you, and you may skip several steps of mathematics. Several mathematical steps can be omitted, but that will be only when you have a concrete knowledge of the calculation. Okay, so I think you have enjoyed this video like the previous videos too, and in the forthcoming lecture we will now see the spin orbit interaction. Okay, thank you very much.